thank you for coming. We'd like to start the open hearing by Mr. Arun Sampati. The title of his PhD dissertation is Exergy analysis of a power plant and evaluation of a silica scaling potential for optimum utilization of high temperature geothermal field. He did research mainly on the Exergy analysis and also the silica scaling evaluation at the geothermal field in the Central Java, Indonesia. So I'd like to invite Arun for his presentation. So please make it about 1 hour.
Okay, good afternoon, everyone. Konnichiwa. First, I'd like to deeply grateful for Professor Ito and Professor Udimitsu to my presentation, my public hearing, public talk today. So first, I'd like to introduce myself. My name is Nugroho Agung Pambudi. I'm belonging of the Laboratory of Energy Resource Engineering, Department of Earth Resource Engineering, Kyushu University. I was PhD student and supervised by Professor Ito. So today, I'd like to presenting about my PhD project. So my PhD project title is Exergy Analysis of Power Plant and Evaluation of Silica Scaling Potential for Optimum Utilization of High Temperature Geothermal Fluid. So actually, this project is the problem of the company, Dieng company. Dieng has the power plant. However, they want to improve their performance, they want to improve their efficiency. But the problem is silica scaling. So silica scales occur in everywhere. In pre-production, for example, in the separator line, in the post-production, for example, in the injection well. So this is a big problem because the company is conscious how to expand this power output, but the scaling is occur. So we want to solve this problem by two methods. First is thermodynamics method with Exergy analysis, and secondly is silica behavior method or silica scaling. So we hope that we can suggest some comment with for company. So okay. I'd like to continue. This is my outline presentation to know deeply understanding about my presentation. So first is introduction. I'd like to connect my project with the realism of the energy in the world. So we know that we have a problem with the energy consumption and energy supply. And then in chapter 2, so I'd like to talking about the Exergy analysis in existing. So in the end, we have the existing single phase power plants, and then we want to know how is the performance there, what is the efficiency there. We don't know actually, and to know. And then in chapter 2, we want to apply the thermodynamics method, the double flow system there, because if we can apply this system, we can improve the efficiency on there. And then in chapter 4 is similar, but the different of the different models. We have the binary power plant and we apply to the existing single flash and to the double flash. So and then in chapter 5 is very important point, right? Because here we want to make a decision maker. We want to make a decision to which is the best scenario for Dieng. So, and then in chapter 6, we give the conclusion and the recommendation. So, this is chapter 1. So, this is maybe too general about the problem in the world. So, we know that the global energy consumption is increased significantly. And then most of them is supplied by the fossil fuel, coal, oil, and natural gas. You can see this one is more 80% that with our supply is from fossil fuel. Actually, this is the problem because we know that sooner or later this energy will be diminishing. will be decreased. Maybe last year, maybe two years ago, is the peak of the fossil fuel. But we don't know, but sooner or later it will be diminishing. So we need more energy security. What kind of the energy security that we can mix to the our energy mix? So because we need more energy secure, so we have two kind of the strategy here. So first strategy is changing the fossil fuel to renewable energy. And then we also have the second option. The second option is to improvement of the existing system, even renewable energy or fossil fuel. So in this case, in our case of these PhD projects, we want to gather both of two strategies. We use the fossil fuel, we use renewable energy because this is the geothermal, and we use the improvement of the existing system in Dieng geothermal power plant. So Dieng will be a study case of our project. So this is the objective of our dissertation. So we make a boundary here. First is thermodynamics, and second is silica behavior. We don't want to go outside of this method. So first, thermodynamic, we want to make the evaluation for single phase because Dieng has the existing of single phase. Now we want to evaluate there because the company actually doesn't know how much the Exergy efficiency there. And then after we evaluate the system, we also want to optimize using the component. So in this case, we give the example for the separator pressures. And then after we know the performance of the single phase, we want to try to apply the double flush system here. We want to know also the performance of the double flush system. And then the similar work, but a different model using battery combined with the single flush here, and the battery combined the double flush here. So all this thermodynamics method to know the performance in development scenario. So we have three cases. One case of the self-optimization using separator pressure, and three cases is using double flush, binary combined with a single flush, and binary combined with double flush. But the thermodynamics method is not enough. Why? Because the scaling problem is occurred is this is the common problem in geothermal power plant, especially in Dieng. I want to let you know later, but how high the silica concentration there. So, and then the other method that in our boundary is silica behavior here. So, in these projects, I did 3 experiments there in field in Dieng. So we went there 3 times, and we make 3 experiments. First is silica concentration along the canal. So we measure the concentration of silica in specific location of the well cap. And then second experiment is polymerization under constant temperature. We want to know how the concentration of the silica changes based on the times. And then the last of our experiment is the particle size of the silica, because silica flow from flash of outlet to the ponds. During their flow, they change the size. So we measure the particle size here. So all this silica behavior to know how is the scaling potential there. And after that, we suggest 2 kinds of this method to know which is the most feasible development scenario for Dieng. This is the chapter 2. This is the chapter 2 about the Exergy analysis, first thermodynamic method that we tried in Dieng. So this is talking about the thermodynamic method and Exergy analysis. This is the first law and the second law of efficiency. So here the objective of the chapter 2 to evaluate the performance of the existing power plants, and then we also make the sensitivity analysis for optimization. So we want to know, is it geothermal power plant in Dieng working on the optimized condition? There, maybe some of you don't know where's the Dieng, but I think from Indonesia, maybe even you are from Indonesia, maybe you don't know where is the Dieng. So if you come from the Jakarta, here is around 500 kilometers from Jakarta, and this is Yogyakarta. So it's around 120 kilometers. So Dieng is located at elevation of 2,000 meters above sea level, so in Java Island. And then a long time ago, Dieng was identified as one of the most geothermal prospect. Some of people said Dieng is gold land because in the past, because there are too many hot reservoirs, for example, hot spring. And then this is the power plant that worked in Dieng. So this power plant is, so actually this is the simplify. Actually this is the well pad. So I might simplify for well pad. Actually there are 5 well pads that work there, but I put only one here. And then the process of energy extraction start from well pad. So this is the production wells. Actually, a single pass of the compressed liquids come from the reservoir, and it goes up and it flows to the well bore, and it flows to the separator. In separator, steam will be flowed to the power hose. It's around 2 or 5 kilometers. This well pad to this power hose, around 2 to 5 kilometers. And then the steam will spin the turbines, and another spin also extract the gas from condenser. Two steam ejector system here, driven by steam, and then turbines will generate electricity. And then the brine from the separator will go to the flusher. And then in flusher is a kind of the separator. It works on the 1 bar pressures is, and then after the flusher, the brine will flow to the canals, and then go to the pumps, and it inject back to the reservoir here. So this is the process on the Dieng geothermal plant. So, and then first, we want to create a simulation for this, and then we need the data. This is the data from the company. So thank you for the Geotipa, the company of the geothermal power plant in Dieng. So we get the some of the data from there, and then this is the data from the environment. So the temperature there is 18 degrees of Celsius, and the ambient pressure is 0.78 bar. So this is the enthalpy. So the enthalpy is very important. So fortunately, I got this enthalpy from the company when when I went there second times. This enthalpy is quite high. Is 1,380 kilojoule per kilograms, and then they work with separator pressure 10.5 bar. And then actually we don't know how much the mass flow of fluid here, but the company gives the data from the main steam here, 48 kilogram per second. And then in the power hose, we know the temperature of the exhaust of the turbines is 38 degrees of Celsius, and the pressure of condenser here, and then the power that need to powering the pump and everything there is 2.6 megawatt, and the power output of the turbine is 24.3 megawatt. Actually, this is very low because the installed capacity is 60 megawatt. So this is the simple thermodynamic process. So if you think about the geothermal will start from the reservoir, and then the compressed liquid will flow to the up, and this is start for flashing in the well bore, point A, and then it flow up and then to the separator, and it will separate to steam comes to C here, and the brine comes to D here, and it will be injected back to the reservoir from the canal and sponge. And then in C, steam will expand in the turbine to E, the exhaust of the turbine, and go to the condenser inlet. And then this is the ideal condition of the isentropic efficiency there. So here the important thing to know is I just put something here. So is the dryness fraction of the separators. So we calculate the dryness fraction here. So from the enthalpy of inlet separators minus the enthalpy of the brines and enthalpy of the steam minus the enthalpy of the brine separators. Then we calculate the mass flow separator here. This is mass flow steam. We know this data from the company, but we don't know this one. So we can calculate this based on the dryness fraction here. So this is the basic of the Exergy, because maybe some of you doesn't know what is the Exergy. Exergy is not energy. So Exergy is the available of energy. So this is the depend on the environment state. So if the system and surrounding reach the equilibrium, so the Exergy is zero, no Exergy. So Exergy is very important to calculating of the efficiency really, but with the efficiency thermal, we cannot see about the opportunity of the system. So this is this basic of equation of the Exergy. So for example, we have the Exergy on specific stream. So we have the mass flow in specific stream and multiply by the difference of the enthalpy. This is the enthalpy of specific stream to enthalpy of the environment or the surrounding or the dead state, and then minus by the temperature of the environment multiplied by the entropy. So this is how we calculate the second law efficiency from the power output divided by the Exergy inlet. So this is the example how to calculate the Exergy in a specific component. For example, this is separator. Separator work to separate the steam and the brine here. It work under specific pressure. So with Exergy, we will know the Exergy inlet, Exergy outlet, and this one, two of the Exergy outlet, and the irreversibility, the losses for each component. And then this is how we calculate one by one of the specific stream. So this is the workflow of our calculation. So we have the data, and then we have the model, and then now we calculate using we use the engineering equation solver. It's like MATLAB, but it's more easier than MATLAB because some property of thermodynamics is included on the ES. So it's like MATLAB. We created the model of the power plant, and we set the equation of each system, and we write the code of the equation inside of the equation, and this is very helpful. So, for example, I give you example for the separator because we have two kind of the parameter, known parameters and unknown parameter. So, for example, in separator, we know the data of the mass stream from the company, and then we know the pressure, we know the temperature inlet, we know the enthalpy, but we don't know how much the dryness fraction because we need to calculate how much the brines, how much the mass flow inlet of the fluid. So we create some code to the ES. And then this is after we create the model and set the equation and helped by the ES, we get the groups, the data, and we created the Grassmann diagram. Grassmann diagram will show the stream of the Exergy. So we calculate that the Exergy from the reservoir is this one, 66.2 megawatt, and then it will flow to the power plant, to the system, and then it resulting on the exergy loss of each component: separator, purifier, turbines, condenser, flusher, and everything. This one. And this is around 40%, 26 megawatt. And then from this stream also, we extract energy to generate electricity here, 24.2. This is the data as well. This is the Exergy efficiency is 36.2%. If we compare this Exergy to the another power plant, it's quite little bit middle, because in the power plant in Iceland, in the Kenya, and another part in the Turkey, it's around middle. And then how much the waste brines? After we calculate, we know that waste brine is 12.6 megawatts, so it's quite big brine. So we dispose to the environment. So in thermodynamics point of view, this is less favorable. So I think we need some kind of the another energy generator to extract this energy into the electricity, because too high losses in brine that dispose to the environment. And then no, we have know that the efficiency there, the performance there, but we still not enough if we can see, is it in being working on the optimized condition or no? So we make one sensitivity analysis in a separator. So in separator, actually the current condition using of the 10.5 bar of the separators, and then we try to make a sensitivity, and we decreasing, we varying the pressures. So from 10.5, we trying the pressure to 1 bar. Then we get that the pressure that resulting on highest power output is 8.6 bar. But you can see that this is not really significantly different with the existing system. So we only get additional power output 109 kilowatt. So it's very low. So so meaning that I think Dieng is close in optimized condition. We cannot change. I think we don't need to change this this pressure, because if we change the pressure, we have to change everything with data from the another component, for example, turbines. So this is the conclusion. So actually this data, that summary that we have talking before. So the total available of Exergy is 66.2. So before we calculate this, we don't know how much the reservoir on Dieng, the Exergy. So we don't know. 66.2 megawatts, and then the power output. This is the data from the company. So this is just on the summary. And also, we know that the Exergy waste that Dieng disposed to the environment is this one, 12.6 megawatt. And then we also calculate, we now understand that Dieng efficiency is 36 in Exergy efficiency. And then the energy efficiency is 11. So now we know that power plant. Before, the company doesn't know, maybe doesn't care. And then the power output in Dieng is close with optimum condition, because only 109 kilowatt that we get from changing the spattle pressure to 6 point bar. So I recommend that this is not, I think we don't need to change this, because this is only additional this. This is too small. So I think now Dieng okay with the optimum condition with now scatter pressure. And then this is the chapter 3. After we make evaluation to the existing system, so we want to know how we can expanding this power output. We have any this is talking about the development scenario using double flush system. So we want to utilize brine that before disposed to the environment waste energy. So now we utilize to get more electricity production using double flush system. So the objective of this chapter is to utilize brine to increase the power output in the end. Now it's 24.3. So after we put the double flush, how much? So we want to know. And then we also want to know the performance of the double flush system, the efficiency of first law efficiency or second law efficiency, and we want to know losses of each component on the system. So this is our proposed designs of double flush. So this is the dash rectangle, red dash rectangle is the additional of the components that we put in the existing system. So if you remember that after the separators, we dispose this brine to the flush directly here and dispose to the environment. But now we send them to another separator. Of course, this separator is lower pressure than this one. We call this one is HPS, high pressure, but in the existing system, this one is called separator only. And then we put the turbine similar, and we also put the another turbine here. And then we send them together with the fluid from this one to the condenser, and all the system is similar. This is the data. So we know the data. This one from this one is the existing data. But how about the data for the additional component that I said before? So for example, on the turbine, before we calculate the turbine efficiency is 82%, but in design we set the design is 85%. This is the design, and then below the power that the power plant needed is similar, 20.6 megawatt. This also used the assumption because we don't know we don't know the data, of course, because they haven't built the double flush system. So we assume that this is similar, and then this one we want to know how much the pressure on the LPS that we should use. We don't know. So the control parameter of the system, of course, the LPS pressure, low pressure separator here, because we don't know, and we want to set the pressure that give the maximum of the power output. And then after we set the data, and then we created the models, we set the data, and we set the equation, thermodynamic equation, Exergy equation, and and the ES help us to make iteration and calculation here. Then, first, we want to know the pressure of the low pressure separator, and then we'll make variation of the pressure from separator from 1 to 10.5 bar. So this is the low pressure turbine. This is the turbine that we add to the existing system. This is the additional turbine. And then actually you can see that 1.77 bar, this is 1 to 170 bar, is the pressure that give the maximum power output. You can see this is the total power output of the DA. You can see this one, this is the maximum. And if we increase the pressure, it will decrease of the low pressure separator and also decrease the total. And this is red curve is the high pressure turbine power output. So this little bit increase. After we know the separator pressure at 1.77 bar, so what should we do? So we make calculation to another component. Here we get the data, and then we created the Grassmann diagram. The available Exergy, of course, is similar with the single flash. And then the Exergy used is this one. From each component, there are additional component, LPS, and then HPS, high pressure separator. LPT, low pressure turbine, and low pressure separator, additional of the component. And then now we get the more power output, 26.16 megawatt. Before only 24.3, now 26.60. So we get additional power output 20%. And then the second law efficiency is increased significantly to 44.04%, and the waste bread now decreased. So the Exergy that we dispose now decreased to 5.44 megawatt. It's around 8%. Before is 19. And before, if you remember, that the west branch is quite high, 16 megawatt that we dispose 12 disposed to environment. So, and then this is the completion of the chapter 3. So we are very happy that if we introduce the double flash to the system, we get the additional of power output 20% to this one. And then we are very happy also because the first and second law efficiency is raised to this one. This is the first law, and this is the second law. And then we can also see that the Exergy loss due to the ion disposal is decreased to 5.44 megawatt. So from the double flash, we can think that additional of component to create the double flash, improve the performance, improve the power output. And then the chapter 4 is thermodynamic analysis of binary. Here we make development scenario by adding binary system into the existing system and binary system into the double flash system. So there here we utilize the brand that being disposed before to environment. Then now we send to the binary system. So the objective of this, of course, we want to evaluate the performance of the system if we add the binary to the existing, the binary to the double flash. This is the proposed single flash combined with the binary. So we consent to the red dash rectangle here. We put the binary system. So the brand from flasher, before in double flash, we send to the separators, low pressure separator. Now we send to the binary systems. This is the heat exchanger, and then we send to the heat exchanger, and the working fluid that work in the binary system will extract the heat from the heat exchanger and generate electricity by binary turbines here. And then in binary combine, this is the data that we get. So this is the similar data with the existing, but here we use design data of the binary, and then the working fluid is set by the N pintan. So we didn't care about another working fluid. We only concern to the N pintan because we want to see the difference performance with this and another system that I want to solve with them. This is the other system that we try to develop scenario. So we concentrate this binary system, and we put this system to double flash. The data is similar with before. This is the data of the existing, and this is the data of design of the binary. And then after we create the models, and then we set the equation, and we solve helped by the ES, we get the result. So this is the result for the performance evaluation. So if you remember on the single flash here before, and if you remember for the double flash here, there are some improvement of the net power output of the first law efficiency and second law efficiency. Now we put the binary to single flash and we put the binary to double flash. If we employ the binary to single flash, the additional of our output is around 3 points megawatts, and we get the total is this one. And then we get additional from binary is 3.65 megawatt. And if we working with the double flash combined with the binary, we get additional per output from the binary, this one, 1.31. So the total now we get 30.47 megawatt. And the first and second law efficiency is increased. So from this point, we know that in thermodynamics point of view, the double flash combined with the binary is the best one to apply in Dieng. But we mentioned again that we didn't care about the cost. We didn't care about the another boundaries, because we make a boundaries for silica and the thermodynamic. So this is for thermodynamic, for double flash combined with binary is the highest per output that we get it. Now the conclusion of this is, we know that before introducing the binary, increase the core output to this, and introducing the double flash to binary, increasing the core output to this, 30. And first law, a second law is improve both single flash combined with binary and double flash combined with binary. So now we enter to the chapter 5. This is a very important chapter on my research, because this chapter will make decision. So even the thermodynamic method give us information that the double flash is the best solution for Dieng. But because Dieng has suffering of the silica scaling, so we put this chapter to make decision. So before, we would like to briefly about the silica scaling problem. So you know, silica scaling is really huge problem. I think in a common of the power plant, silica is a problem only there. But Dieng is special case. I'm reading on the paper that Dieng is quite really high of the concentration of silica, and I will show you later the value. But I think this is very dangerous situation if we cannot manage this silica scaling. And then if you want to ask that what happened if the silica scaling there, of course if the silica scaling there, they will decreasing, for example, of the hole of the pipe. With decreasing of the pipe hole, it will decrease of the flow capacity. We can extract fluid from the reservoir, and then we also cannot send brine to the injection reservoir, especially when the injectivity on the reservoir is decreased. So we cannot send. If we cannot send this brine, so we cannot produce the fluid, because we have to send back this fluid to the reservoir. So if we want to create development scenarios, so we should really consider to the silica scaling potential, because we want to make the energy extraction is sustainable. This is the objective of this chapter. So because they have include 3 experiments, so we want to know the effect of the canal and ponds, because again is applied this system. And then we also want to know about the characteristic of the size, particle size of the silica. And then after that, we want to make decision selecting of the most feasible development scenario of work plan for Dieng case. So this is the figure of the canal. If you can see, this is the canal, and then this is the flasher. The brine flow out here. I think this is not not really clear, but I think you can see here. So brine flow out from the flasher and goes to the canals, and then the canal used in dyeing, the objective canal in dyeing to deposit the silica. So during it flow, it will deposit on the wall of the on the canal. And then what happens if the scaling occurs there? This one. You can see that this is pipe, injection pipe, and this is the scaling. This is around 3 months. 3 months. So every 3 months, the company have to clean this. Of course, this is costly. This is not free. This is cost. So they have to cut the pipe. I think every 3, 4, 6 meters, and then they clean mechanically, and it happens continuously in the end. Then after this one, this is the ponds. So brine will flow to the ponds, and this pond will let the brine for several hours before it inject to the reservoir. This is the pump, and this is the pump pipe. This is the pump, and suck the brine and send to the injection well here. But the problem is this one. This is the pipe here. You can see that the pipe will sometimes broken because this is scaling there. So we made the experiment. This is for first experiments. Silica concentration along the canal. So actually, Dieng has several. So we have several well beds. So we working on the 3 well bed. So this is the typical of the canal system. So this is the flasher that I showed you before. It is flow here and goes to the ponds. This is the distance around more than hundreds, and then another canal here. This is from a flasher, and it goes here and goes here, and then back. This is the back end of the flasher, and here, and this is the pump. And this is the another type of the canal. So this canal function is to deposit of the silica before. And then we take sample from each location. So we take the sample in specific location. We want to know the trend of these silica concentration. And then this is the second experiment. I think this is the third times that we went to Dieng before in 2013. So this one is similar. This is the experiment design. This one, we have the container here, and then we hang this one with the rod, and then we put to the canals, and we keep the temperature similar with the temperature of this one and constant, 85 degrees Celsius. And then we put the brine here from the outlet of the flasher, and then we take sample every several times. And this is the analysis method that we use after we get the samples. We analyze cation and anion using ion chromatography, and another method is we measure the temperature and the pH inside. This is inside. This is in laboratory, and then we also measure the monomeric and total silica concentration in laboratory using the molybdenum yellow method, and we also measure the particle size of the silica. This is the first result from the chapter 5. This is talking about the chemical analysis. So here we know that I said before that I will show you how much the silica value on here. This one, average 1,400. And then if we compare with the another power plant, is this one, is the Fushime Otake and Hachogaru in Japan. And I heard also in the Patuha, sort of the Bandung, it's similar company with the Dieng, is only half 600 ppm. And also heard from Gunung Salak, from Chevron, also around 600. So Dieng is special case. The concentration of silica is really high. And then this is the temperature and pH measurement. So this is from well pad 1 and this is from well pad 3. This is longer than the well pad 1. So the temperature is decreased from 86 to 73. And also for this one also decreased for 85 to 47. And the pH, this is the very interesting because two kind of pH difference. In well pad 1 is pH is around 6. Neutral around 6, and then well pad 2, this is well pad 3 is 6, and then well pad 1 is more acidic. This is around 2. And then this is the result for silica concentration along the canal in well pad 1s. So we very happy because 2 times we went there and we see the situation is different. So when we first time going there, the acid treatment is working there in the end. Yes, this is the result. And the second times we went there, the non-acid treatment, the acid treatment doesn't work. So this is non-acid treatment. So we can see that this one is sorry for the last sample here. So it a little bit strange, but we see the trend. We see the trends. So the total, and then the polymeric silica is small. The difference between monomeric and total. And if you can see on the similar well pad, this is quite a bigger chance for the total, and the polymer of silica, polymerized silica, is also high difference, this one. And then, you see that from fresher is 1,400 and this one 1,000. So it's quite different. So we assume that because of the non-acid treatment, the position is occurs between the separators and the flasher here. Then this is the result of one of the results. Just give one example. There's too many results here. So this is the particle size of silica based on the number. So if you can see the red curve, well pad 1 is 0 distance here, and well pad 1 is 145 distance. Then the silica is shift to the right, meaning that silica is growth, because you know the peak, this one, 10 nanometer, and then this one around 100. So this is a big change of the silica size. So meaning that during its flow from the flasher to the ponds, the silica grows. And this is the experiment on the polymerization under a constant temperature. So from the initial condition, this one, so from 0 minutes, and then every 5 minutes, 5 minutes, 10 minutes, 20 minutes, 30 minutes, 40 minutes, until 180 minutes, we take the samples and we measure the silica concentration. You can see that this is significantly decreased on first 40 minutes, this one, and after that it decreased. It's quite constant. So meaning that the changing of the silica concentration doesn't change much after this one. So this is the point if you want to design of the canals. And then this is the very important of the data that we get. So in this diagram, we can see the basic scenario for the DN. So this is the solubility of the amorphous silica. This one is proof of the amorphous of silica. So in single flash, this one is single flash. The silica concentration, we assume that this is from the separators, one average 1,200 ppm, and the solubility of the in this temperature is 900. So there are excess silica here. So this is the scaling potential that can be occurred there. And how about if